for z in S1, and f of z1 is f1 of z for z in the unit circle. And finally, f of 1t is equal to b for 0 less than equal to t less than or equal to 1. So this f, as he says, the corresponding maps f0 and f1 from S1 to x are homotopic relative to base point 1 in S1 and b in x in the sense that there's a map, big F, like that, continuous, satisfying the data I wrote on the board. And he says, conversely, if you do have that f0 and f1 are homotopic as paths from the circle into your space in the sense I just defined, then you can construct a homotopy for the corresponding loops based at B. So this is interchangeable. In other words, let me write it this way. Alpha 0 is alpha 0 homotopic to alpha 1, interchangeable with f0 homotopic to f1 in the sense that we've defined here. This means that f0 is homotopic to f1 in the sense described for functions from the circle into the space versus for functions with fixed endpoints on the space, the homotopy we talked about last time. So we have either way of kind of looking at homotopy, either as maps from the unit interval or as maps from the unit circle, depending on which is more convenient to your purpose. All right. I really wanted to calculate the one. Where'd that stupid calculation go? Oh, man. How far is that? Oh. Son of a gun. Oh. Shnikes. I really want to prove to you guys that the fundamental group of the, the punctured plane is the integers. Oh, has he relegated that to an exercise?
Yeah, he mentions it on the top of page 119.
It would be, shown in section 5. Section 5 is so far away. I want it today. Come on. We need the path lifting lemma. Man. We got some work to do before we can actually calculate the fundamental group of the punctured plane, right? There's like an hour, like at least an hour of theory between where we are and where that is. So annoying. I really wanted to do that. I thought I could. Oh, I'm an idiot. I should have spent less time talking to Dr. Sprano today and more time looking at your topology. My apologies. It's really too late to topologize, though. So I feel like it was not the most legitimate use of that joke, but anytime I can work it in. So let's move on to section 4. I'm sorry, this is kind of boring in a sense. The payoff is later. This is part of it, so we have to work through this. The larger point here, though, is in the next chapter we learned about higher homotopy. And higher homotopy studies, this basically in some sense is looking at, homotopy is something like looking at putting circles in your space and seeing if you can deform circles, something like that, roughly speaking. Higher homotopy looks at things like torus, or no, spheres, right? Yeah, Sn. And looks at like putting like a little sphere in this face and seeing, can you fit a sphere? Can you deform the sphere? Like, how does that work? Like, you know. So the higher homotopy is looking for sort of sphere-shaped regions in your space, roughly speaking. And then there's three spheres. There's like, you know, yet higher homotopy type that looks for like maps of three spheres into your space. All right, that's the next chapter. But we have to start with this. Again, the larger point of what we're doing is trying to see if we can, you know, use algebraic, abstract algebra to say something about topology. At the end of this, we'll actually have, I think, enough to prove that Rm and Rn are not homeomorphic. As I mentioned before, a surprisingly technical thing to prove. So induced homeomorphism, homomorphisms. All right. So suppose you've got two pointed topological spaces, and this actually is a good. I like this is a good thing for the last 10 minutes of class. This goes back to your question about category theory, Jonathan. Like, when are we going to talk about category theory? The answer to that question is now. So pretty much, if we have a map F, a continuous map from pointed space Y to a pointed space X. That was not what I was expecting. With, you guessed it, f of c equals to b, then what we want to do is to show that this map induces a homomorphism f star. We can induce a homomorphism f star from where? From fundamental group of y based at c to the fundamental group of x based at b. This is the aim of this section, is to show that if you have a continuous map, it induces a corresponding homomorphism on the fundamental groups. And he says the map f star will be defined in the obvious way, making a path gamma in y corresponding to a path f composed with gamma in x. Just homomorphism. F is continuous, not at the moment just continuous. So let's just draw a picture of what's going on here, okay? So here's y. Here's x. We're taking a path in a loop in y where, well, actually we can, before we even think about a loop, we can think about a path, all right? So a path over here, alpha, and this is a function, this function f goes from here to here, right? There's alpha is actually like this, so this is from the closed interval from 0 to 1 up to there is a path, right? And so we take f of that, f composed with alpha would be this, right? Is that right? So I hit alpha up to here, and then I feed it to f. It takes me over to there. So if I have a function going from y to x, I can take a path in y, alpha, and I can convert it to a corresponding path, f composed with alpha in x. And if I can do it for a path, I can do it for a loop. So essentially, the map is just this f star of a loop alpha is equal to f composed with alpha loop. Right? And let's see, what does he prove in this? His lemma 4.1. He's like x and y topological spaces, f a mapping from y to x a map, alpha 0, alpha 1 paths in homotopic paths in y with endpoints fixed. Then f composed with alpha naught and f composed with alpha 1 are paths in x that are homotopic with endpoints fixed. So his first point, his lemma 4.1 simply proves that this mapping is well defined. So Dr. No, this one, if we have that alpha, his lemma 4.1 simply says if we get alpha 1 equals to alpha naught, that implies that f composed with alpha 1 is homotopic to f composed with alpha naught. So that proves that this mapping f star, which is a mapping from loops at C to loops at B, is in fact well defined because it's independent of the representative for the loop. All right? So that's the first order of business. Then his corollary 4.2, let y be a convex subset of Rn. Let y and y1, y naught and y1 and f be a map from y to x. Alpha and beta paths from y to y naught and 1. I don't understand this corollary. So I guess he's just applying lemma 4.1 to the case that y is a what? Convex subset of Rn. Do you guys follow what he's saying? And this is like y, a subset of Rn. He still has f mapping over here to a continuous mapping to x. This is a topological space. It's not necessarily a subset of Rn, right? Y is convex subset of Rn. Y0 and y1 and y. All right. And f a map from y to x. Alpha and beta are paths from y0 to y1. Oh, okay, I got it. So this is alpha, this is beta, right? Then what's he saying here? He says then f composed with alpha is homotopic to f composed with beta over there in x with endpoints fixed. Now, hold on just a second here. He didn't say that alpha and beta were homotopic. So how is this a corollary to lemma 4.1, which I haven't actually written on the board? Precisely. Since y is convex, that means that this, of course, tells us that the homotopic class of alpha is equal to the homotopic class of beta, which means then that we can apply the lemma. And hence, this is a corollary. Okay, good. So what's he do now? Let's see here. He defines he defines f star on alpha as we did, right? And then what does he prove about it? What's he prove? He proves that it's a homomorphism, right? So, and he argues f star of alpha beta is equal to f star of alpha, f star beta. So it's a homomorphism, right? And he also shows that it preserves the inverse, right? And what's that? I mean, the following thing is not required for it to be a homomorphism, right? But, I mean, it's nice that it's true, I suppose. Right? Oh, I know why this is needed. I think it's actually, this is needed. I don't know. This is needed because if you have this, what I just wrote down, that the f star of the reversal f star of the inverse loop is the inverse of the image of the loop, then if you put that together with the one above, it gives you the constant. I mean, that implies the one below, namely that f star of the, where are our loops starting? Wherever our loops are, C. So f star of the loop, the constant loop C, is, you know, what is it? The constant loop f of C. So if you go back to our original setup, that would be B, you know? What that says is it says that, remember that the constant loop is the identity for the group. So part of being a group homomorphism is it has to map the identity to the identity. This says that the identity of loops based at C maps to the identity of loops based at B. Right. Yeah, you can, exactly. That follows from this and that. Also true, yeah. Yeah. Right. So I guess this is just good pedagogy, is pointing out like it works as it's supposed to, right? And then the theorem is what? If you have pointed topological spaces x, b, y, c, and we have a map like we do, then f star is a homomorphism of the fundamental groups as advertised, right? And furthermore, if you had additional maps, if you had, you know, yet another map, so this was F, right? And then you also had a G, say going to, I don't know, Z. You pick a letter, any letter. Oh, how about A? Right? There must be some reason we're not using A, and I'll regret this, but then in this context, we could compose what? F composed with G, right? Would be a mapping from where? What's that? I can't do maps today. G composed with F, thank you. I trust you guys. That would go from where? That would go from Y, the pointed space YC, over here to the pointed space ZA, right? And you can prove, in fact, that G composed with F, the induced homomorphism, is in fact G star composed with F star. Oh, yeah. Well, I have my letters reversed, but, you know, same idea. And in particular, If we take the identity map, the star of the identity map is just the identity map again. And corollary 4.4, if we have a homeomorphism, all right, if we have a homeomorphism, if F is not just a continuous map, if it's also one-to-one onto with continuous inverse, if it's a homeomorphism, then F star is in fact an isomorphism of the fundamental groups. So this is, I think it starts to be a good example of the kind of thing you see in category theory. So the idea of category theory is something like, taking, I don't have the language ironed out here right off the top of my head, but this is something categorical which is going on. We're trading a morphism in the category of topological spaces, a homeomorphism, for a morphism in the category of groups, which of course is a group isomorphism, right? And this kind of interplay is at its heart something that the kind of thing we try to describe carefully in category theory. There are theorems that you come across in math which are true in all categories. You have this strong sense of deja vu as math students that you've seen this before. When sometimes you come across a theorem, like it's the same theorem, right? And category theory makes that sense of deja vu precise. All right, that's my 30-second version of category theory. But there's different kinds of categories. There's there's topological spaces. There's we can study vector spaces and their structure. We can study groups and their structure. We can study Lie algebras and their structure, Lie groups and their structure. There's something, this star thing, right? Trading F for F star, that somehow connects. That again, it's a way of, going from the topological category to the group category. A similar example in manifold theory. You could have something like a manifold, another manifold, a function, f, and then there's something called the tangent space to M. There's the tangent space to N. And you know what? There's a differential, which is also sometimes denoted F star. And in the same way that if this is a smooth map, in fact, if this is a diffeomorphism, this ends up being an isomorphism of vector spaces. That's the same kind of pattern. And it also, if you have the composite, there's a chain rule. Now, my notation is not awesome here, but with stars, it looks exactly the same as what's in Gamelin right now concerning the connection between continuous maps and the homotopy. This has a name, this F star. Do you guys remember? This is the so-called push forward in manifolds that I know. This is something. It's got a name. Oh well, I'm going to have to leave it there because I got to go. Oh! You guys need to give me a refund. I went over.